Okay. Okay, are we ready? Okay, so I have two propaganda pieces in the very, very beginning, which I forgot to say. One thing that you might notice if you look in the list of people who have been sponsoring this workshop, there's this thing called COFI that you probably never heard of before. This is a new institute in Puerto Rico. It's the Colegio de Física Fundamental e Interdisciplinar de las Américas. It's an initiative that started out at Northwestern University, and they have resources for workshops and collaboration meetings, and we're trying to work towards getting more resources for paying things like students and postdocs as well. And it's just getting started. If you hear about it and if you get invited, Puerto Rico is really, really nice. I strongly encourage people to go visit. They've survived the hurricane, and it's a great place to go. So anyway, that's one piece of propaganda that I wanted to make. The other one is this is something that Orlando forgot to say yesterday. So they're going to have this very nice school in Campinas in December on experimental aspects of neutrino physics, and they will have a very nice list of lectures discussing lots and lots and lots of different topics in neutrino physics that range from phenomenology to more details of how experiments work and so on. Oh yeah, yeah. So they have a lot of money, that's what he's saying. So write that down if you like neutrino physics. Okay, so what I want to do is to start talking about matter effects. So one thing I want to do very quickly is to talk about the phase difference that I mentioned last time, and I didn't go into details at all because I'm going to be using this a lot. So the statement that I made the last time is that if you have some neutrino mass eigenstate at t equals 0, and let's say that you do the calculation in the reference frame of that neutrino, so that neutrino is just sitting there at rest. Because it's an eigenstate of the propagation Hamiltonian, it propagates as an eigenstate of the propagation Hamiltonian, which means imagine it's some neutrino number 1. So it's just going to get a phase factor that's proportional to this. And of course, if I'm doing this in the rest frame of the neutrino, this phase factor would be something like the mass of the neutrino times the proper time of that neutrino, for example. Okay? And this is the sort of step 0 of the quantum mechanics. The question you can then ask is, if I do this in the laboratory frame, my m times tau gets changed into p dot x, where this is et minus p dot x, like that. And this is the phase that I'm interested in. Again, if I have a mass eigenstate, this phase is completely immaterial. So that means if I start out with a mass eigenstate, after some time or some distance has elapsed, if I ask the question, what kind of a neutrino is this, it's still the same mass eigenstate. So if I start out as a neutrino number 1, and I ask what's the probability that I measure it as a neutrino number 1, that probability doesn't change, and it's always 100%. That's just basic quantum mechanics. So hopefully that's clear for everybody. Now, the thing that's interesting is if I start out with a flavor eigenstate, that's a linear combination of mass eigenstates, and each component gets a different phase. So the thing that I care about the most is not the phase, but it's the phase difference. And the phase difference is related to this object here. And let me just tell you the approximations that I'm making in order to rewrite this phase difference in a way that's proportional to the neutrino mass squared. So I'm going to do this very quickly. And I will say this is kind of a cheat, but it gives you the right answer. And it kind of makes sense. So let's go with that. Okay, so that's the idea. So let's say that the neutrino is traveling in some fixed direction, say the z direction or the, whatever your favorite direction is. And let's say that it goes some distance L. And let's assume that the neutrino travels really fast. It travels at the speed of light. That's a great approximation. It always works. Neutrinos are very light. So that means that the time and the distance are the same. So that means that my phase, let me write it here. So my phase to a good approximation is E minus P times the distance L. Okay, so that's my approximation. Again, if the particle is massless, in this way that I'm doing the calculation, the energy and the momentum have the same magnitude, so this phase is 0. And again, like I said, if all the phases are the same, they actually don't mean anything, so getting a 0 phase should not concern, it's not a problem. But the mass is not 0 by assumption, so this phase will be not 0. So let me rewrite this in the following way. I can multiply and divide by E plus P. So if I do that, I get E squared minus P squared divided by E plus P times L. Okay? Now, E squared minus P squared is the mass squared. And I'm assuming that the mass is really small. So it's approximately true that E and P are the same. Okay, so the difference is really small. That's what I'm trying to calculate. But if I'm interested in the sum is basically 2 times the energy. Okay? So does everybody understand these steps? Oh yeah, the L is missing. So this means that my phase factor, for my purposes, in the laboratory reference frame, assuming the neutrino is ultra-relativistic, it's proportional to m squared over 2L, which means that my neutrino mass eigenstate as a function of time will acquire a phase that looks like that. Okay? So that's the assumption that I'm making. And nobody asked about this yesterday evening, but believe me that this works. And let's just run with that. And this is the other step that I mentioned, is that if my plane, if my time evolution of a mass eigenstate looks like this, then this really looks like a non-relativistic quantum mechanical system, where instead of the L, instead of calculating something varying as a function of time, my states depend on L, and the eigenvalues of the Hamiltonian, or the energies, are m squared divided by E. So because my solution looks like that, I can rewrite my problem as a Schrodinger equation, which is what I do up there. Okay? So because I know that this is what the solution is, I can rewrite everything as a Schrodinger equation, and then I can take advantage of that to write down what's the Schrodinger equation for the electron neutrino and the muon neutrino. So the Schrodinger equation for the mass eigenstates is very simple. It's the thing at the very top. But I can rewrite this in the flavor basis, because again, remember, the flavor eigenstates and the mass eigenstates are linear superpositions of one another. So I can change bases as much as I want. So I get this equation here at the bottom, assuming that there are only 2 neutrino flavors, nu e and nu mu. And then I have a Schrodinger equation that looks like that. And when I say Schrodinger equation, it really looks like a non-relativistic, a first-year quantum mechanics problem of a 2-level system that we know how to solve. And how do we solve that? The way that we solve that is we have a Hamiltonian. So if I want to solve the problem, given some initial condition, I have to look at my Hamiltonian. I have to diagonalize the Hamiltonian and find the eigenvalues and the eigenvectors. I rewrite my states in the basis of eigenvectors of the Hamiltonian, and the eigenvalues of the Hamiltonian tell me what the phase factors are. Okay? And I'm making the assumption that we are all infinitely familiar with how to solve that problem. Okay, so is that fine for everybody? So again, I can convert the neutrino oscillation problem, which is true for ultra-relativistic neutrinos, but I can convert this into a very simple non-relativistic 2-level system quantum mechanics problem. Okay? And the intuition that you want to have is the thing that plays the role of the time is m squared over E. I'm sorry, the thing that plays the role of the energy is m squared over E, and what plays the role of the time is the distance that the neutrino propagates. Okay, so is that fine? So now we're going to talk about these problems, because we want to worry about what Orlando mentioned yesterday, which are matter effects. And I'm going to try to introduce the matter effects using a very different language from what he used. And of course, the answer has to be the same. It's just a different way of looking at it. So I will use a little bit of more sophisticated language, but you shouldn't be worried about that. So the thing I have at the top is the Lagrangian for neutrinos propagating, and I'm including the interaction, so not propagating, the Lagrangian for neutrinos, and I include the interaction of the neutrinos with the electrons. Okay? So the term on the second term that's included there, that's just the Fermi interaction. It describes how neutrinos and electrons interact. If you actually know about this, oh yeah, and you remember what that interaction looks like, you might be, so if you really have great memory, you could be concerned about two things. One is this term here doesn't look right, because the term should look like a neutrino converting into an electron. So this term here should be neutrino electron, and this one should be electron neutrino. But I've taken the liberty of rewriting that in a different way, and you're allowed to do that, so that's fine. If you have great memory, you might remember that this number here is wrong. It's not 2 square root of 2, but it's square root of 2, or something like that. But of course, this is a consequence of this rearrangement. And finally, the last thing which I want to point out is that usually this interaction has some 1 minus gamma 5s in it, which it does. But I'm including that by saying that these fields here are purely left-handed. So the E sub L is the electron field multiplied by 1 minus gamma 5. So that's just so that people who actually understand everything don't get confused. If you don't understand this, then you wouldn't get confused. Now, what we would like to do now is to do the very first exercise that you do in quantum field theory, which is, so somebody tells you, here's my quantum field theory Lagrangian. What you do now is to solve the free particle problem, and you calculate what the one particle states look like, and they look like plane waves. So if you remember, there's a one particle state that you can define. The equation that you get out of that is the Dirac equation, and the solution are the plane waves multiplied by these Dirac wave functions. Okay? So hopefully that sounds vaguely familiar to most people. And again, this is very important. So I want to redo that exercise, except that I want to include the possibility that I have electrons in the medium. This is not something that we're familiar with, because we seldom talk about this. But basically, when we define the one neutrino state, we end up at some point, because we're going from a quantum field to a state, we're calculating some expectation value of something in the vacuum. Normally, it's something like a creation operator of the neutrino operating on the vacuum that gives you the one neutrino state. So if I go through this calculation more carefully, but now I want to remember that there are electrons around, then for the most part, when you're going through this exercise, all of the interaction pieces don't contribute. They will kind of cancel out the leading order, and that's why you get a free particle propagating. But if I have a background, then I have to calculate this expectation value of this electron current here. And again, for the most part, if you're propagating in vacuum, this object is 0, if there are no electrons to begin with. But if I have an electron background, this is not 0 anymore. But it is something that I can calculate. So this is the expectation value of my electron fields. And if you do the calculation, basically what this here will measure is, again, this is for the benefit of people who remember quantum field theory. This is E bar gamma mu E. So I want to calculate the expectation value of that. Whatever this is a 4-vector, because there's a gamma mu here. And then I have a gas of electrons. So I have to ask myself, what could the components of this 4-vector be? And in particular, one thing you can very quickly convince yourself of is this thing has a space component. And what would the space components of this thing be? And if my gas of electrons is a bunch of electrons at rest, I can't think of any space component that this thing could have, right? Because this is a bunch of electrons at rest. They're not going anywhere. That means that there's no direction in space where anything exciting is happening. So just by a symmetry argument, you can argue that this thing here can only have the 0 part, right? The gamma 1, gamma 2, gamma 3 part has to be 0. By the way, if you think about it a little bit more, if all of my electrons were moving in some direction, then you could have something that would be proportional, for example, to the current of these electrons moving in that direction. But I don't have any currents, so the space part has to be 0. So if I look at the time part of this is this object here. If you remember what bar means, it means E dagger gamma 0. Gamma 0 squared is 1. You guys should know this better than me because I haven't taken this class in a very long time. So this looks like this. Okay, so this object is equal to this object. Now, this you might remember because it's very important. But E dagger E is the electron number operator for the field. It's not totally true because you have to integrate that over space. So this is the electron number density operator. So to make a long story short, this object here is the electron number density. So it just counts how many electrons you have per unit volume. And it only has the 0 component. And now this is left-handed. Remember, this is the left-handed current. I have a bunch of electrons at rest. And if you want to think about it that way, it's not a polarized electron gas, it's unpolarized. So if you want to think about it, half of them are left-handed, half of them are right-handed. Doesn't matter what left and right means, but it's half and half, right? And I only care about half of them. The other half don't count, so I get a factor of a half. So just to say, so basically if you start out with this equation, the equation for a one neutrino state is the Dirac equation plus some weird piece that has to do with the fact that you have electrons in the medium. Okay? But this is just a differential equation. It's kind of like the Dirac equation where I have this unusual piece that has a gamma 0 in it. This gamma 0, by the way, is from this gamma mu over here. So even though it looks weird, it's something you can solve. And again, the solution will also be a plane wave if you make the right approximations, including that this object here is small. And if I neglect the neutrino mass, my regular plane wave has a dispersion relation which is E equals P, so, or E squared minus P squared equals 0. But I get a modified dispersion relation which is instead of E equals P, I get E equals P plus this object over here. Okay? So does everybody at least follow what the exercise is supposed to be? And it's a simple exercise. And of course, because this thing here has units of energy, and because my energy is equal to the momentum plus something, that's called a potential. Because if I was talking about in terms of a particle in the presence of an external potential, this is exactly what a potential looks like. This is called the matter potential. And it's proportional to how strongly the neutrinos interact, which is the Fermi constant, and it's proportional to how many electrons I have in the medium. Now, the electrons are not special. I can do the same thing with protons or neutrons or whatever your favorite particle is that happens to be in the medium. And the only last thing I want to mention here is this plus or minus sign. And what happens is, if I were this, so again, if you remember, this field here describes both the neutrino and the antineutrino, right? That's one of the nice things about this economical quantum field theory, is that you get two particles for the price of one. So the question is, if you go through the exercise for asking what is the equation for the antineutrino as opposed to the neutrino, and you go through that when you learn about the Dirac equation and the electron field, then you get exactly the same equation except that the sign flips. Now, why does a sign flip? This is easy to at least convince yourself it makes sense, is the fact that this interaction here is a vector interaction, right? So this is, in your Lagrangian, you have a neutrino, gamma mu neutrino dotted into something. This looks a lot like the electromagnetic interactions. So if I write the electromagnetic interactions for the electron field, the thing that shows up in the Lagrangian looks in spirit like this. So instead of this being, it would be the electron current dotted into A mu, which is the photon field. And when I work out the differential equation in the presence of an electric field, I get the Dirac equation plus a term that's proportional to the electric field, which is identical to this in spirit. And of course, if I have the electron field, the electron has negative charge, the positron has positive charge. All of that information is encoded in that Lagrangian. So that's just to say that you do have this plus and minus charge, and you can trace that all the way back to the fact that you have this vector current there. So the fact that the electron piece was something with a gamma mu in it gives you this plus and minus charge. If you had a current that was a scalar current, you wouldn't get plus or minus. Both the particle and the antiparticle would have the same sign. So that sign is related to the gamma mu. So when you go to this exercise for this problem here, the same plus or minus sign will show up. Okay? Yes? The gamma 5? Oh yeah, the gamma 5 is included and it doesn't do anything. So it's not the gamma 5, it's the gamma mu and the work that you have to do to rewrite the differential equation for the antiparticle. If you remember, when you do the antiparticle, if you're brave enough, you have to do a charge conjugation operation and rewrite everything for the charge conjugated field. And when you do that, some terms change sign. It's that sign. I think that sounded right, so that's good. Okay. So for our purposes, all that we care about is that now when the neutrino propagates in matter, the dispersion relation changes. So instead of it being E squared minus P squared equals M squared, it's going to be something that in the limit where the energy is very, very small, where the energy is really large, you get this extra contribution here. So now if you remember what I wrote down on the board here, the thing that I care about is this E times T, and the thing which I used very, very strongly to calculate that my phase looks like M squared over 2E, I used the neutrino dispersion relation. So because the neutrino dispersion relation has changed, that propagation piece will also change. Okay? So, but remember that I mapped my problem into a non-relativistic quantum mechanics problem. So when I do that, this matter potential also shows up in my non-relativistic quantum mechanics language, and my equation now changes into a different equation. So my neutrinos propagating as a function of L has the piece that I wrote down before, but it acquires a new piece. And there's a lot of information that goes into this. The really important information is, at the end of the day, all that you care about are the electrons in the medium, because certain contributions cancel out, and more importantly, because we're talking about the electron and the muon, it's the electrons that are different, right? Because you have electrons in a medium, the electrons speak to the electron neutrino in a way that's different from how it speaks to the muon neutrino. And because this is a quantum mechanics problem, I can add and subtract anything proportional to the identity matrix to my Hamiltonian, and my physics doesn't change. This is a very important, very simple thing to know, but basically, if you take your Hamiltonian, you can add, 1,000,000 multiplied by the identity matrix. All of your eigenvalues will shift, but the physics doesn't change, because the effect of that is just multiplying your entire wave function by a phase which is not observable. So I can take advantage of that to write down my Hamiltonian in a way that makes my life easy. So that's how I can get to write this Hamiltonian this way. Okay? So even if you didn't follow all of this, if we start from this Hamiltonian, we can now solve neutrino propagation in the presence of matter, and it's a quantum mechanics problem, and it's not even one of the hard ones, it's one of the easy ones. Having said this, this can still be a very hard problem, because as the neutrinos are propagating through matter, it is possible that the density, so again, the key thing is that this is proportional to the electron number density in the medium. So it is possible that the electron number density in the medium changes as a function of position. If that's the case, then you have a quantum mechanics problem where the Hamiltonian depends on time. Okay? Because you're all old, you've all gone through these problems in your classes. Because that's what you talk about in, say, quantum mechanics in graduate school, which you have all taken. Right? So you know that there are lots of techniques for addressing some of these problems if some approximations hold and so on. Okay? So is that very clear? And again, if you talk to your neutrino physics friends, all that they do for a living is solve that equation. or they solve the 3x3 version of that equation, which is harder, or the 4x4 version of that equation, which is a little bit harder. The 3x3 one is already really annoying. That's why we don't do any 3x3 stuff, because it's very hard. But the 2x2 one is really easy, so we know how to do that. Okay? But that's what people do for a living. And I'm going to talk about what some of these solutions are. And again, this is the equation that I want to solve. I rewrote this in a different way. And of course, the way to solve this is just like how you solved it before. You have a Hamiltonian. You find the eigenvalues and eigenvectors of the Hamiltonian. You express your initial conditions in the basis of the eigenvectors of the Hamiltonian. And then you can answer whatever question you want. You know how to do the L propagation of your neutrino. So you won't be surprised to learn that I can write down the neutrino oscillation probability in a way that looks exactly like what it looked like in vacuum. So it's some amplitude and some sinusoidal function if this A parameter is a constant. So if the A parameter is a constant, I can solve this problem exactly. And the only thing that changes is that my amplitude now depends on the A parameter, and my oscillatory phase also depends on the A parameter. Okay? And I wrote down for you what this delta M here is. By the way, in vacuum, this delta parameter, which I think I wrote down there, is delta M squared over 2E. Why do we get delta M squared? Because remember, one neutrino in vacuum is M squared over 2E. The other neutrino acquires a phase M2 squared over 2E. I only care about the differences of the phases. That goes like M1 squared minus M2 squared over 2E, which I write as delta M squared over 2E. So that's where that is. If I have these matter effects, things get changed by something that's proportional to this A parameter. I'm not going to dwell on this too much. I'm going to show you what these functions look like for different values of A. There are a couple of things that are very important. One is there are some magic values of A where, for example, this term here cancels out. So imagine that A minus delta cosine of 2 theta vanishes. If that happens, delta M is delta squared sine squared of 2 theta. And then in that case, you can convince yourself that your amplitude becomes as large as possible, which is 1. That's this resonance that Orlando was talking about. The downside of that is that this delta gets as small as possible. So that means that your induced oscillation length gets very long. Right? So the oscillation length is the inverse of delta. And that leads to the effect, for example, that Orlando showed yesterday about this resonant behavior, which of course, remember the way I write it, and I like to write it this way, remember the delta goes like delta M squared over E. So this resonance happens for a very specific value of E, and you're off resonance for the other values of E. Okay, the other thing that's really important is that neutrinos and antineutrinos are now different, because the A is positive for neutrinos and negative for antineutrinos. That's this plus and minus sign that I emphasize. So that means that as neutrinos propagate through matter, neutrinos and antineutrinos behave differently. And as you can say, this is not a CP violating effect. It's actually a CPT violating effect. It violates the CPT theorem, not really, but it's not a surprise. It violates CPT because your neutrino is propagating in a CPT non-invariant background. Okay? So if the neutrinos propagate through electrons, if you do a CPT transformation of that system, that would be an antineutrino propagating through positrons. So neutrinos propagating through electrons is the same as antineutrinos propagating through positrons. We don't know how to do an experiment where the neutrinos propagate through a positron background. That's very, very hard. So we only get to we live in this CPT violating planet where you only have matter in it. So we have to do experiments in this very inconvenient place. So that's how that happens. And again, this is very important. Neutrinos and antineutrinos behave differently. Now this, on the other hand, is very powerful in terms of making measurements. Because that means if you make a measurement and you see that neutrinos and antineutrinos went their separate ways in the oscillations through matter, that provides you some information about, for example, whether this combination here, delta times cosine of 2 theta, is positive or negative. That's a physics question you can ask, and you can get the answer to that question if the neutrinos propagate through matter. You can't get the answer to that question if they propagate through a vacuum. So this is what these probabilities look like. So in vacuum, they would look something like this red line here. If I turn on the matter effects, you either get an enhanced amplitude and a bigger wavelength, as I advertised, or you get a reduced amplitude and a reduced wavelength, depending on what's the relative sign of A and delta times cosine of 2 theta. Okay? This is very important. There's a fun fact, which is also very important, is that if you look over here, when L is very small, these matter effects don't do anything. Okay? This is very important, and all of your neutrino friends know this, is that if you want to see the matter effects, you have to go a long enough distance. If you don't go a long enough distance, there's not enough time to see the matter effects. That's easy to see from staring at the Hamiltonian, and I will let you worry about that. But again, from your intuition of quantum mechanics, you should be able to convince yourself that that's actually true. So, now we want to talk about neutrinos coming from the sun, and sadly, all of this thing that I just wrote before does not apply for the sun. And the reason is very easy to understand. The neutrinos were born inside of the sun, where it's really hot and really dense, so you have lots of electrons, and they make their way out of the sun until they get to the end of the sun, where it's not so hot, and there are no electrons. So they see a density of electrons that changes very dramatically as a function of distance, as a function of position. So you have to learn how to solve this problem when your Hamiltonian depends on time. And nature was very kind to us because nature made the problem really easy to solve. So we don't have to learn a lot of atomic physics to solve this problem. We had to learn a little bit of atomic physics, but that's okay. You know, we can always learn something new, as long as it's not very hard. So let's go back to this problem here. And again, this is the Hamiltonian that I have. And let's ask the easy question, which is, what are the eigenvalues of this Hamiltonian? I can solve that. And there are 2 eigenvalues. And of course, the eigenvalues depend on this number A. Okay? And I do want to mention one thing which I'll come back to a lot. We're going to look a lot at this Hamiltonian for the next 10 minutes or so. And the key thing is that this Hamiltonian is the sum of 2 parts. And one part is proportional to this number A. The other part is proportional to this thing delta. So what really matters a lot is whether A is much bigger than delta or the other way around. And that will give me the behavior of my system in these 2 extreme regimes. And I know, for example, that when A equals 0, I get pure vacuum oscillation, so I know how to handle that. And we're going to talk about what happens when A is really large. And so if I calculate the eigenvalues of this as a function of A, this is what they look like. This is called a level crossing diagram for people who actually have done atomic physics, for example. And this is the large eigenvalue as a function of time. This is the small eigenvalue as a function of A. And of course, this is called, we also call this the heavy branch and the light branch. Okay, so these are the eigenstates of the Hamiltonian. You can all calculate this. It's diagonalizing a 2x2 matrix. We all know how to do that. It's actually not even diagonalizing, just calculating the eigenvalues up to a constant that we don't care about. So this is useful because it gives us a sense of what are the eigenvalues of the Hamiltonian as a function of A. And if I'm interested in solar neutrinos, it also tells me what are the eigenvalues of the Hamiltonian as a function of where the neutrino is inside of the sun. So, you know, when you don't have any A, the eigenvalues of the Hamiltonian are just the m squareds over 2e. So this here would be m1 squared over 2e. This would be m2 squared over 2e. Okay? By the way, you can say, why did you bother to plot this for negative A? Because I can. And because the negative A is how antineutrinos behave. So if you look at the other side, that will tell you what the antineutrinos are doing. Fortunately for the sun, there are no antineutrinos, so we don't have to care about that. But for other systems, this is a question that people ask. Okay, so this is my eigenvalues as a function of A. And I will tell you a fact, which is we're going to be interested in the regime where inside of the sun, A is really large. compared with delta m squared. Okay? So if we happen to be in that regime, then the electron is born when A is really large. And then something interesting happens, which is, let's go back to the Hamiltonian. Remember, this is the Hamiltonian in the flavor basis. So in this basis, the electron neutrino is the 1,0 state. The mu1 neutrino is the 0,1 state. Okay? Now let's look at this Hamiltonian when A is really big. So if A is really big, what are the eigenvectors of this Hamiltonian? Now the eigenvectors. The eigenvalue is A and 0. That's correct. But what are the eigenvectors? It's 1, 0, and 0, 1, because this is just a diagonal matrix. Right? So if A is really big, I can pretend this piece doesn't exist. So I just have to diagonalize a diagonal matrix. So that's easy. Done. And I know the eigenvalues are A and 0. And the eigenvectors are the electron neutrino and the muon neutrino. So this means when the neutrino is born as an electron neutrino in a very dense medium, it's actually an eigenstate of the Hamiltonian. And we know how it propagates. It just propagates. It does nothing. Nothing funny happens. So now we are prepared to understand how electron neutrinos propagate out of the sun by making a last approximation that you just have to trust me. And that's what's called the adiabatic approximation. And what happens is, if your system is not changing very fast, that means the eigenvalues and eigenvectors of the Hamiltonian are not changing very fast, then if you're born as an eigenstate of the Hamiltonian, as you propagate through this time-dependent Hamiltonian, the system starts to deform, but you have enough time to always stay as an eigenstate of the Hamiltonian. And I assume that half of you have heard about this before. There's something called the Landau-Zehner effect in atomic physics, which is associated to some of these pieces of this. And it has to do with these time-dependent Hamiltonians. And the adiabatic approximation is a very powerful approximation that allows you to solve approximately problems with a time-dependent Hamiltonian. For our purposes, this means that if the electron neutrino is born as an eigenstate of the Hamiltonian, if this approximation holds, it will stay an eigenstate of the Hamiltonian as A is changing, which means that as it exits the sun, so it started out as this eigenstate of the Hamiltonian, when A is this other number, it'll be a different eigenstate of the Hamiltonian associated to the same related eigenvalue. So the eigenvalues are continuously related. So by the time you get to A equals 0, which is when the sun ends, you are still an eigenstate of the Hamiltonian. And in this case, we know what the eigenstate of the Hamiltonian is. It's one of the mass eigenstates. Okay? So if all of these conditions hold, that means that A is really big inside of the sun, and the adiabatic approximation holds, then a neutrino born inside of the sun will get to the end of the sun as a mass eigenstate. Not just any mass eigenstate, the heavy mass eigenstate. Okay? So is that clear? By the way, the antineutrino does the opposite. The antineutrino would be born here, and it would exit the sun as the other mass eigenstate. So very, very different. Okay? So are we very clear on that? That's all you have to know about solar neutrinos. That's what solar neutrinos do, most of the time. But the key point is that you're born an electron neutrino, you exit the sun as a mass eigenstate. Mass eigenstates are eigenstates of the Hamiltonian in vacuum. That means that all the way from the surface of the sun to your detector, nothing happens to your neutrinos. They don't oscillate at all. They stay happily as a mass eigenstate all the way to the detector. So neutrinos from the sun actually don't oscillate at all. It's all a lie. Everything happens inside of the sun. But this is very important because if you exit the sun as a mass eigenstate, then you have a nu2. That's an eigenstate of the Hamiltonian. It doesn't do anything as it propagates anymore. Now I want to ask, what's the probability that that's an electron neutrino when it hits my detector? That's this object here, squared. And fortunately, we know what this is. This is one of the elements of the mixing matrix. And it's equal to this number here. So it's one of the elements of the mixing matrix. This is really exciting And people got very excited about this because this element is some number between 0 and 1. And it could be very small. It could be whatever you want it to be between 0 and 1. And you get an answer that's qualitatively different from vacuum oscillations. Remember, vacuum oscillations go like 1 minus sine squared of 2 theta sine squared of delta m squared. And unless the delta m squared is really, really small, you often have averaged out oscillations. Averaged out oscillations go like 1 minus 1/2 of sine squared of 2 theta. And the smallest that number can be is a half. So if you have averaged out oscillations, and you have 2 neutrinos, on average, you will lose at most 1/2 of the neutrinos, unless you get very lucky. You know, that means if your oscillation length fits just perfectly, then you can miss a lot of neutrinos, because you could have the sine squared theta. I mean, the sine squared of delta m squared piece to be 1, but that requires a very special conspiracy between the energy and the distance. And by the way, when people were talking about the solar neutrino problem, people figured out what the delta m squared had to be so that one neutrino oscillation length was about 1 astronomical unit. That's a delta m squared of below 10 to the minus 10 electron volts squared. And that was called the just so solution, because the delta m squared was just right that you got 1 astronomical unit for your neutrino with 10 MeV. And it was a great solution, but it turns out to be wrong. But that was something people talked about. So this is everything we need to understand about this phenomenon. Life gets a little bit more complicated in different ways. So one thing that can happen is that maybe the electron neutrino is not exactly a Hamiltonian eigenstate. It has a different component of the other Hamiltonian eigenstate. We can correct for that. The other thing that can happen is that maybe this adiabatic approximation doesn't hold. So how do I fix that? And people have figured out, Landau solved that problem 100 million years ago. So it's a solvable problem, but it's probably hard because Landau solved it. But people know how to do it. So these are the ways that you can violate this. And you can go through the details. This will be on the slides. And this is how you make life a little bit harder. But the spirit is exactly the same. Again, the things that change are whether the electron neutrino really is a Hamiltonian eigenstate or not, or whether you can violate this adiabatic approximation. And the way that we do that is really stupid, but it's very effective. What we can do is, I said that this guy is born here and ends up over here. But then you can say, what if that doesn't happen? What if you're born here and you end up over here? You associate a probability for that to happen. That's called the crossing probability or the jumping probability. What's the probability that you start out over here, you start moving along this line, and then you jump to the other curve? And that tends to happen over here, by the way, when the levels are really close to one another. That's why people care about level crossing. So the jumping probability is a number, and that turns out to be a great approximation for this problem. Okay? So these are all the elements that go into this. And at the end of the day, this is what you expect your survival probability as a function of energy to look like. And I'll go through this very quickly. When the energy is very when the energy is very large, the delta m squared over E is very small. So the matter potential is very important. So this whole story that I told you before works really well. So that means that your survival probability is proportional to this UE2 squared. Don't worry about what the numbers say there. This number here is almost UE2 squared. There's some extra wrinkle to this that we don't care about that has to do with 3 flavors. So, and it's a constant. It's just UE2 squared. It's a number. And this is true as long as the energy is large enough. If the energy is really small, then the delta m squared over 2E is really big. So the matter potential relative to that is very small. So you can throw away the matter potential. Those neutrinos behave as if they're just oscillating in vacuum. And you can check that the oscillation length is so big, so small compared with the Earth-Sun distance, that those oscillations average out. So your survival probability is just like 1 minus a half of sine squared 2 theta. Again, the corrections to these have to do with these 3 flavor effects. It's a very tiny correction. And again, it's a constant. So as long as the energy is small enough, You can forget about the matter effects. Your oscillation probability is just averaged out oscillations. Doesn't depend on anything, it's just a number. And of course, you've learned the behavior of the curve over here. You learned the behavior of the curve over there. For some energy, those two curves have to meet. And you can pick your favorite way of getting them to meet, and it kind of looks like that. So you don't have to solve. This is when the problem is hard, but you know it kind of looks like that because it can't do anything crazy, right? Curves don't do stuff like that unless something spectacular is happening in your equation. And nothing spectacular is happening, so you're fine. So this is what these curves look like. And this turns out to be how solar neutrinos oscillate. And again, this is the same curve back again, but I have some data points. The really important data point is from the SNO experiment. The SNO experiment is making measurements over here. And it tells you that 1/3 of the neutrinos of electron type survive. So the electron neutrino survival probability is 1/3. That means that your UE2 squared is 1/3. That's your fit to the data. Then you have things like the gallium experiment that see the PP neutrinos and the low energy neutrinos. So they're measuring all the way out here, and that number is going to be 1 minus 1/2 of sine squared of 2 theta. So with those two data points, you get to fix what sine squared of 2 theta is. And in order to fix the delta m squared, you want to make sure that you are in the fully MSW. Oh, by the way, this whole business is called the MSW effect. I should have said that, I forgot. So the MSW effect is very effective here. So we want to be in the large A limit, or the small delta m squared over E limit for these energies, and we want to be in the large delta m squared over E limit for these energies. And that tells you what the delta m squared is supposed to be. There's a fun fact, which is in the region where something interesting is happening, we don't have any data, which is very disappointing. And it's great for theorists because they can invent crazy models where something bad happens in the region where we don't have any data. And sure enough, these models are allowed, unless something bad happens in the region where you have data, and then the models are ruled out. But that's kind of how theorists work. That's a very good question. I'll say a little bit more about that. So the new kid on the block, which I guess is already 10 years old or so, is what's called the Boric SINO experiment. And what they did was to add points around here, including this measurement of the beryllium-7 neutrinos. And they also attempted a measurement of what are called the PEP neutrinos. And these are neutrinos that cover this intermediate region here. And they're starting to say something about how this function is behaving. Sadly, they're not there yet. This is a log scale now, that's why it looks different. The other way you can get to this turn up here is, remember I said about the super K and the SNO experiments? They have a high energy threshold, but they can lower the threshold by analyzing their data better and doing a better experiment. And they work very hard to do this to try to see this rise of the survival probability from this end. There's a fun fact, which is the SNO experiment worked really hard to do this. And this is their data on the right. So you expect the curve to go like this. The data actually go the other way. But the error bars are very big. So we didn't see the rise in the survival probability. It actually went the wrong way. But everything is consistent, so don't worry about it. Everything is fine. But it's very disappointing that this went the wrong way, just from the aesthetic point of view. And of course, oh, of course, yeah. It's not relevant, but yes, there are models that do this, yes. And of course, when you look at this, it looks very fishy. But you want to keep in mind that these error bars are ridiculously correlated. So once you start going down, you're going to go down. That's, once some fluctuation went some way, then your whole spectrum kind of thinks, in many quotes. So there's nothing too suspicious about that. So this is the solar neutrinos, and that's how they were resolved. Orlando showed you this before. We managed to do this experiment on Earth to see these oscillations using reactors. And this is a really amazing experiment that I think should have gotten the Nobel Prize, but the Nobel Prize Committee doesn't agree with me. This is called the Camlin experiment. This is a reactor experiment in Japan. And from the solar neutrino data, we guess what the delta m squared is supposed to be. Orlando wrote this down yesterday. It's almost 10 to the minus 4 electron volts squared. A reactor neutrino has energies of, say, several MeV. So you can estimate what kind of an experiment do I have to do on Earth with a 10 MeV neutrino in order to see these solar oscillations. And the baseline that you get is about 100 kilometers. So that means if you do an experiment with a reactor and you put your detector 100 kilometers away, you should see these solar oscillations. This is the Kemlin experiment. Now, for those of you who know about experiments, you should laugh and say that this is a totally crazy proposition. Because, you know, the flux of a nuclear reactor is isotropic, so the neutrinos go everywhere. So the reactor neutrino beam is a really bad beam because the neutrinos go everywhere. And as your detector gets further and further away, your flux falls off like 1 over r squared. So if you put your detector 100 kilometers away and you didn't have a lot of neutrinos to begin with, you're going to get no neutrinos at your detector. So doing this experiment is totally crazy unless you build the right country. And that's what they did. So this experiment is done in Japan before the tsunami. That's also very important. So timing is everything. So without offending anyone, this is what Japan looks like. And Japan used to get almost all of its energy from nuclear power. So there are a lot of nuclear power plants in Japan. And nuclear power plants rely on water for cooling. And Japan is an island, so there's a lot of water around. So you put a lot of your nuclear reactors happen to be around here. So if you put your detector right here, it turns out that you have a lot of nuclear reactors that happen to be about 100 kilometers away. That's what happens. So that's what they did. That's the experiment. And this is the measurement of the experiment when you take the expected flux of neutrinos from all of the nuclear reactors around you, including some nuclear reactors in South Korea. They don't talk about North Korea. And then you divide that out by your data. So the data divided by expectations, and they get this absolutely amazing result. So not only the answer is not 1, so your electron neutrinos are disappearing in a way that's predicted by your experiment. You know, it's a function that looks like that. It's a little bit funky because you have to average over all of the different nuclear reactors, and they're not all at the same distance. So they all have some average distance that you have to work out. And then if you do that, you get also this very, very pretty oscillatory curve. I've said this before and it's not true, but this is probably the first very nice oscillation curve we ever got out of a neutrino oscillation experiment. Because the solar data don't have any oscillations. In the atmospheric experiments, if you work on your data just right, you can get it to look like an oscillation in some very small region of the oscillation space by looking at these angular plots that I showed you before. Yeah. That's a very good question. You mean, what about the solar neutrinos? Very good. So I should have said this. This is a reactor neutrino experiment. They look for electron antineutrinos, which is a thing that comes out of nuclear reactors. This experiment does not care about electron neutrinos. It does not see them at all. It only sees electron antineutrinos in just the same way that Reines and Cowan discovered the neutrino to begin with. So it's exactly the same experiment with a bigger detector and a lot of nuclear reactors. By the way, there is a planned experiment to measure neutrinos from a nuclear reactor 50 kilometers away from just one nuclear reactor. And if you do that, you get a much better measurement. And that's in China. It's called the Juno experiment. That's being built right now. That's a really, really hard experiment. And it requires an experiment that's much bigger than the Kemlin experiment. And they have this really super powerful Chinese nuclear power plant as well. This is in units of L over E. You mean here? There's a dot here. So remember, 50 means nothing because this is an L over E. So any experiment will give you a spectrum, right? Because you have an energy spectrum coming from your nuclear reactor. And even if the L is fixed as a function of L over E, you can make a nice plot like that. And that's what they're going to try to do. And they're actually trying to see something much harder than just these oscillations. Yeah. They're not, yeah. These are neutrinos produced in a nuclear reactor, but just like the solar neutrinos are supposed to oscillate, these guys have to oscillate too. It's the same physics. So once we learn the parameters from the solar experiments, we can ask, how else do I get to see the same phenomenon on Earth? And I can do that with reactor neutrinos and a baseline of about 100 kilometers. Yeah, they have this very complicated way of oscillating, but that behavior is still governed by the mixing angle and the delta m squared. It's just that the dependency on the mixing angle and the delta m squared is much more involved. But once you know those two numbers, you can ask, what else do these numbers do for me? And they do these types of oscillations as well. Yes? Why does, oh, because of the, it's probably, so I won't give you the right answer, but I will tell you what could be happening. And usually what they do is some experiments will have the sizes of the bins be such that the vertical error bars are about the same. So if you don't have enough events, this is in the large L over E means a small energy part of the spectrum. And that's a region where, for example, backgrounds are quite high. So they have to contend with that. And then over here, as L over E gets very small, you start running out of flux. So your electron, your reactor flux is bound. Yes? So the overall number of neutrinos, I won't remember, but it's of order 1,000. It's not a high statistics experiment. The high statistics experiment is if you try to do the same thing, but you put your detector 1 kilometer away instead of 100 kilometers away. Then your flux goes up by 100 squared. Then you're talking. And that's the experiments that were done more recently, because they wanted to see the same effect, but associated with a much smaller oscillation length. And I'll mention that very briefly. So more questions on this. And you can quantify that. I do this as a very old slide, but it's a nice slide. So if you take all of the solar data and you interpret that in terms of 2 flavor oscillations, these are the values of the parameters that you need. So your mixing angle is in some range, your delta m squared is in some range. You do the Scanlon experiment. You also get some allowed regions of the parameters. This is old, that's why the allowed regions look funny like that. Literally funny, because this is a smiley face. So there you go. And what's really amazing, of course, is that if you look at the preferred region of the parameter space for those 2 experiments, they agree quite well. So again, this is a very, very strong evidence that we understand that this is the phenomenon that's going on. Because these are completely different experiments. One is neutrinos coming from the sun, 1 astronomical unit away. The other one is antineutrinos produced in a nuclear reactor 100 kilometers away. And the detectors are completely different. Everything is completely different. And those 2 data sets are explained by the same phenomenon, and the same parameters explain all the data. So this is very, 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 very important. And again, you have a delta m squared, which is about 10 to the minus 4. Okay. So the last thing I'll talk about in terms of fitting data and so on is, let me remind you of the atmospheric data. So that was the other exercise that we did, that I worked you through in a lot of detail. In order to fit those data, you need a delta m squared of 10 to the minus 3 electron volts squared. In order to fit the solar data, you need a delta m squared of about 10 to the minus 4 electron volts squared. So those numbers are clearly different from one another. And of course, all of these analyses are done using 2 flavors. Because there are 3 flavors, you can definitely accommodate 2 delta m squares which are very different. Because you have 3 numbers they define two differences of masses squared, and those numbers don't have to be the same. So you can see how the picture will hold together. There's a nice question you can ask, which is, so we do have this delta m squared, which is 10 to the minus 3 electron volts squared. And this delta m squared is telling me how muon neutrinos are disappearing. The other delta m squared, the one that's 10 to the minus 4, that's telling me how electron neutrinos are disappearing. And we know that as far as this frequency here is concerned, the electron neutrinos weren't doing very much. But you can still ask the question, do the electron neutrinos see this other oscillation frequency as well? So if I do an experiment, and there are two oscillation frequencies, in principle, everybody should oscillate according to both oscillation frequencies. So you can ask, why doesn't the electron see this other frequency? And the reason turns out to be because the amplitude is small. But it's not zero. So we did more reactor experiments to look for electron neutrinos oscillating at this fast oscillation frequency, or this small wavelength. And that was a triad of different experiments. It's the double show experiment in Europe, the Reno experiment in South Korea, and the Diabei experiment in China, next to Hong Kong. And this is a really amazing experiment. It's a reactor neutrino experiment where they built a bunch of detectors right next to the nuclear reactor, a bunch of other detectors a kilometer away, and they were asking the question, do the electron neutrinos oscillate according to the fast oscillation frequency, or the small wavelength? What's really amazing is that we know what that number is. So the delta m squared is some number, and that's why we built the experiment at the distance that we picked, because that's where the effect is largest. So this is a single parameter fit, because I knew what the frequency was, and the only thing I didn't know was the amplitude, and these are the data points. So this is in the far side, this is in the near side, and this is the frequency that's given to me by the atmospheric neutrinos. And you notice that if I pick the amplitude just right, I can go right through these points. And again, this is a single parameter fit. I'm not adjusting the frequency. The frequency came from a totally different experiment. So again, if these ideas are correct, I get this great agreement. If the model were wrong, there's no reason why these things should match just perfectly like that. You can convince yourself that this is actually a very powerful statement, although not everything is included in this picture. There's a lot more information about looking at the spectra as well. And again, what you get out of this is that you can measure the amplitude, and notice that this is a very small amplitude, right? So the amplitude here, this is a suppressed 0. So this is 0.9 relative to 1. So this effect is less than 10%. It's about 8%. So that takes a much harder experiment. One thing which I didn't emphasize enough, we kind of got lucky with the neutrinos in general, because all of these mixing effects are really large. You know, mixing angles are like a third or a half. And that's why we got to see these gigantic discrepancies relative to expectations, as long as we could wait long enough. So if you can do an experiment where the baseline is long enough, the effects will be really, really large. Except for this one. This one is small. And this one took a lot of very sophisticated experimental planning and a lot of information from other experiments for you to be able to see a 10% difference in your neutrino flux in a neutrino experiment. This is also very important for people talking about next generation experiments, and we're going to have a colloquium on this in the afternoon. You know, the first results we saw were really big, so they were very hard to miss. The next round of results are at the 10%-ish level. So we've gotten smart enough to see a 10% effect. The next thing we need to do is to do a 1% measurement. And that calls for a qualitatively different kind of experiment. And that's what people are working on today. That's just the mixing angles. And I'll try to put this together into a picture. And you can ask me that question later. First of all, you want to learn what they are, period, because they exist. And then how much smarter you are at the end of the day is a different question. That's a much harder question. So, to summarize, we can fit all of the data with two frequencies pretending that there are only 2 neutrinos for any particular data set works really well. And this is how the data looks like. So solar neutrinos are electron neutrinos oscillating into some combination of mu and tau with a delta m squared of 10 to the minus 4 electron volts squared and a mixing angle of about 1/3. Atmospheric neutrinos are nu mu to nu tau with a delta m squared which is 10 times bigger and a mixing angle which is about 1/2. It's called maximal mixing. And finally, we've seen electron neutrinos disappear at this delta m squared associated with a very small mixing angle, and the mixing angle is about 2%. The thing that you see in the experiment is 4 times that, so that's the 8% effect that I talked about. So this is how we explained everything. And it turns out that, again, nature was very nice to us because in principle now you have to go back and redo all these exercises now assuming that there are 3 neutrinos. 3 neutrinos is the same story in spirit. It's harder to do in practice. So now your mixing matrix is 3 by 3. You now have 2 mass square differences. They're called three masses squared and 2 mass square differences. It's m1 squared, m2 squared, and m3 squared. And of course, you can talk about m2 squared minus m1 squared. And you can talk about, say, m3 squared minus m2 squared. And of course, there's a 3rd mass square difference, which is this one. But this one is not independent from the other 2. Because it's obvious, hopefully, right? So you have those mass square differences. You now have this 3 by 3 unitary matrix. So instead of just there being one mixing angle that parameterizes the matrix, it turns out that as far as oscillations are concerned, you end up having 4 physical parameters that make up this matrix. You can pick those parameters to be whatever you like, but there have to be 4 of them. And the parameters that we normally pick are 3 angles. They're called the theta 1, 2, theta 2, 3, and theta 1, 3. And then there's another parameter which is a phase. It's a complex phase. It's called delta. And the delta lives, for example, in this parameter over here. So this parameter is theta 1, 3 times some e to the I delta. Okay? You can pick whatever parameters you like. You don't have to stick to those. But of course, it has to be a unitary matrix. These are the parameters that we all have agreed on. If you are coming from learning about rotations in classical mechanics, they are very, very similar to this. It's a 3 by 3 orthogonal matrix that defines a rotation in space. And if you didn't worry about this delta, that matrix would also be an orthogonal matrix. And it's parameterized in terms of one of the many different definitions of Euler angles, for example. Although I think the Euler angles are some very specific choice, which I can't remember right now because I'm giving a lecture. If you ask me later, I'll probably remember. They might be these, but I don't think they are. Doesn't matter. So the last thing I want to, so I'll show this. This is impressive. So if you take all the data, you can fit that. And these are the numbers that you get by combining everything as of a few months ago. The screen is shaking. There you go. Okay. Oh, okay. Good. So this is, I'm not going to go through all these numbers. I do want to mention one last thing which is very important, which is the following. So we have these masses M1, M2, and M3. So I call them M1, M2, and M3, but just giving them a name is not good enough. In principle, I have to tell you what they are so that you know that M1 is this number, M2 is this number, and M3 is this number. And if I could do that, everything would be fine. Just like the electron mass. You know, if I just say the electron mass, that doesn't mean anything. The reason it means something is because we know what that number is. So I call those masses 1, 2, and 3, but we have to define what those masses are. Sadly, we don't know what their values are. But we can still define what they are relative to one another, or in some way. And I have to do this in order to actually make this whole picture well-defined. Otherwise, the picture is not well-defined. So the way that we define these masses is, first of all, we know that one delta m squared is much bigger than the other. So you can ask yourself, how can these masses be ordered in such a way that there are 2 differences of masses squared, which one is bigger than the other? And there are two ways you can do that. It's this way or this way. Okay, so here's 1 delta m squared, which is small. Here's 1 delta m squared, which is very big. And the third one, which is not independent, is about as big as this one. Okay? And I can draw the picture this way or that way. If you don't believe me that this is the only way to do it, I invite you to try, and you will convince yourself that this is the only way to do it. Okay? So there are these two different ways. And now I want to tell you who are M1, M2, and M3. There are many choices you can make. The one that occurs to everybody is the obvious one, which is to say, maybe M1 is the lightest one, M2 is the second lightest one, and M3 is the heaviest one. And that would be a very reasonable choice, but it's very, very messy to do that, it turns out. So we do it in the following way. So we look at these states. The ones that are closer together are 1 and 2. Okay? And 2 is heavier than 1. So that means that this is 1 and this is 2 if the picture looks like this. And this is 1 and this is 2 if the picture looks like that. Okay? So this is my definition of my masses. Of course, whichever one is left is number 3. So if the picture looks like this, they're ordered 1, 2, 3. If the picture looks like this, they're ordered 3, 1, 2. Okay? The reason we do that is because it allows us to fit the mixing angles in a way that depends very, very little on whether the picture looks like this or looks like that. That's why we do that. Okay? So the last thing is there is an observe. So this is my definition. So in this definition, you notice that this delta m squared 2, 1 is a positive number. That's always true. And that's by definition. So that's not a physics question you can ask. It's a fact. On the other hand, delta m squared 3, 1 is bigger than 0 here, and it's less than 0 here. And that's an observable. Okay? And this sign, plus or minus of the delta m squared, tells you whether the picture looks like this and looks like that. Okay? Now, why am I talking about this? I'm talking about this because right now we don't know what the right picture is. So and the language we use to talk about that is to say that if I could measure whether this number is plus or minus, I would figure out which picture I have. So that's often how this question is posed, and it's part of the language that we use. And if you look at this table, this ambiguity is included here in this thing called the ordering. So this ordering here, 1, 2, 3, is called normal. And this ordering here is called inverted. It's not called abnormal. It's just inverted. It's not the right one. Now you can ask, why is this one here the normal one and this one here the weird one? And I don't have a good answer, except that this one looks normal. And it's 1, 2, 3, which is the normal order. But if you look here, there is a fit for the normal ordering and a fit for the inverted ordering. And as far as all the data we have access to today, these two are virtually indistinguishable. They are both good fits to the data. Okay? So since I'm running out of time, I do want to talk about summarizing things. So this is another way of looking at these fits. I do want to emphasize there is this delta parameter that I talked about. We haven't been able to measure that, but it's a very important parameter because that number is equal and opposite when you compare mixing of neutrinos and antineutrinos. So again, if the mixing matrix of the neutrinos is U, the mixing matrix of the antineutrinos is U star. It's the complex conjugate matrix, if you want to think about it that way. So since delta is the only thing that makes the matrix complex, it relates those two objects like that. What I said is not totally right, so don't quote me, but that's the spirit of what this delta means. And what experiments want to talk about and want to measure is what is this delta, and they want to make sure it's not 0 or pi, because if it's 0 or pi, then your matrix is real. So neutrinos and antineutrinos oscillate in the same way. If it's not 0 or pi, then neutrinos and antineutrinos oscillate differently. That means that matter and antimatter are doing something different. And that's violation of CP. So right now, we're starting to say something intelligent about delta, but we haven't gotten to a point where we can rule out that it's 0 or 180 degrees. And again, what we're going to hear about in the afternoon is what kind of experiments you have to do in order to see, in order to shrink these error bars significantly and convince yourself that delta is not 0 or pi, or maybe it is and we just don't know yet. Okay, so if you give me a few more minutes, let me just close the picture of neutrino oscillations and just say something interesting. So these are these mass hierarchies. Orlando talked about these pictures before. This is a way, these are supposed to be the masses squared, and either this ordering or that ordering, they're both allowed. And these colors here are supposed to represent the entries of the mixing matrix squared. So the fraction of this bar, which is colored blue, that's a u tau 3 squared. So this is giving you information about that matrix. So so u tau 3 squared is about a half, u mu 3 squared is about a half, u e 3 squared is very small. That's the 2%. And if you look at these numbers, that's what they are. Let me point some fun features here. One is if you look at the way I've drawn this picture here, every bar has the same fraction of green and blue. And we would like to know if that's actually true or not. And that's related to measuring one of the mixing angles called theta 2-3 better, so that we can see whether things are more green than blue or vice versa. That's one very important question that we don't know the answer to. The other one, of course, is we don't know whether the picture looks like this or like that. We don't know about CP violation, which I've already mentioned. And if you're a theorist, you ask other fun questions. There's another interesting fact, which is if you look at neutrino number 2, here or here, you notice that it's very democratic. It kind of looks like one of these European flags, where the amount of green, red, and blue is about the same. The question is, does that mean anything? Probably not, but for some theorists it means a lot because they spend a lot of time working on that. So but more seriously, by looking at these numbers, you can be asking yourself, is there some hidden message here in these numbers? Or is nature trying to say something more fundamental through these funny numbers? And we've been asking those questions for a long time in particle physics, and I think it's safe to say we haven't gotten a very good answer yet, but it's still subject of a lot of research. We've asked those questions about the quarks as well, and we haven't gotten a very good answer either. I do want to finish up by saying that we're probably going to hear about all these measurements that have to be made in the afternoon. But there's one piece of physics, or I guess a philosophical statement that's very important, is that when you do these experiments, especially these next generation experiments, we often describe the experiments as making a bunch of measurements to complete the picture. But I think we're not there yet. I think our job is not to complete the picture, but it's to find out if that's the right picture or not. And Orlando talked about stereoneutrinos before. So that's one way in which the picture could be incomplete. So the real goal of next generation experiments is to complete the picture. And we're not there yet. And I will conclude, this is the last thing I'm going to show today. I guess not, but okay. So this is from another talk. But anyway, so you want to remind yourself of the fact of how much work we've already done with the quarks. So if you're familiar with the Standard Model, you learned a lot about quark mixing. And the quark mixing and neutrino mixing is the same physics. It's not different physics. It's the same physics. It manifests itself in a very different way. But from a Standard Model-centric perspective, that part of the neutrino physics is also present in quark physics. And in the quark sector, again, if you've been following the story, and I haven't told you about the quark story, but quark physics took off, I guess, when we started discovering a lot of particles all of a sudden. All the mesons, pions, kaons, rho mesons, weird baryons, and then in the 70s we discovered charm particles, and then we discovered B particles and top particles, and there was a big mess, and that all organized itself in some magic way. and we ran into this mixing phenomenon. And until today, people were doing experiments with B mesons to measure all of these mixing phenomena. And one thing you should be asking yourself is, aren't we done already? We've been doing these experiments for 3 decades. And they're really expensive experiments, and you have to learn the names of all these mesons, and it's a mess and so on. So why are we doing this? We've measured these numbers really well. And the reason we're doing it is to make sure that the picture is right, that we're not missing anything. So what we do in the quark sector is, we measure the mixing angles in 20 different ways. And we measure CP violation in 5 or 6 different ways. And the reason we do that is not to show that we can, but it's to ask the question whether the picture is correct or not. Because if you measure the same thing in 2 different ways, you only get the same answer if your model is right. If your model is wrong, you're not allowed to get the same answer by measuring the same thing in different ways, because you're using the model to combine those 2 results into the same observable. So in the neutrino sector, what we really would like to do is to measure these mixing phenomena in lots of different ways and see if the different ways of making the measurement give you the same answer. That's easier said than done, because neutrinos are kind of the opposite of quark physics. So again, if you're familiar with these quark flavor physics, quark flavor physics is really, really messy because of QCD, just to summarize things. So QCD is very hard. Nobody understands QCD. Doing calculations is very messy. On the other hand, in quark physics, you do have 100 observables. You can measure all different kinds of things, and they're all very interesting, and they all carry the same information packaged in a very different way, so you can ask if your model is correct or not. In neutrino physics, and I say this in many quotes, the observables are very easy. It's just oscillation probabilities. They can all be calculated perfectly, and there's no strong interactions. It's all weak physics, the physics we understand very well, and the tricky part is nuclear physics, but let's not talk about that. The observables are very, very clean as observables. The problem is we only have like 2 observables, or 3, or 4, and that's it. So we can play this game only so far. And that's the challenge that we have, is to how do we invent, in quotes, new observables to test the formalism. And I think for the last lecture, I'll concentrate on talking a little bit about what some of the measurements for the future will be, and I'll see what Stefan has to say in the afternoon, and then I'll try to talk a little bit about theory as well. Okay, so I'll stop. It's the time to stop, right? I'm not reading the clock wrong. Okay, good. So I'll stop here.
And you write down the rest of the questions for today afternoon and tomorrow afternoon, right? So
the delta value can explain the asymmetry between matter and antimatter?
So why don't you ask that question later in the question session? Yeah, that's a very good question, yeah. And the answer is very complicated. So I don't want to talk about that for 5 minutes now. But yeah, so it's a great question, and I'll try to, if you ask the question again, I'll maybe give more information.
Start with that one. Another question?
Oh.
Yes.
It's a quick question. So why, in the matter effect, why are you allowed to neglect nucleons? And charge currents, for instance?
So there are 2 different things that happen. One is the electron and proton contributions cancel out, and the neutron contributions are flavor independent. So they are diagonal, and they are proportional to the identity in my Hamiltonian, because they affect electrons, muons, and taus in the same way. So I don't need to include that. However, if you have a stereoneutrino, as Orlando talked about yesterday, and you weren't here, so you didn't hear that part, you have to include the neutrons as well. So again, if you're propagating through neutral matter, there's another effect you should think about, but you don't have to worry about that, it turns out, because it cancels out. And then the neutrons are proportional to the identity, so you don't have to include that. So, and when we include the electron contribution, you should also include the neutral current contribution for electron scattering, But that one is the same for electron mu1 and tau, and that's why I don't talk about that. So the piece of the Lagrangian that's relevant is only the W exchange piece. It's not the Z exchange piece. That cancels out between the electron, the muon, and the tau. So anyway, that's the answer to that.
Great, so we'll break for lunch. Just a reminder that today we are back earlier. We are back at 2 because we have the IFT colloquium, which is part of all of the school. So see you all at 2. After the colloquium, we'll have, well, when the people not from the school leave, when we go to the discussion session, then we'll take a group picture of everyone. So, okay, so see you later.